Good morning to all. I am Kajal from BSc Chemistry Honors final year. In today's session, I have prepared an audio lecture for visually impaired student for inorganic chemistry, which is from Kapilaa publication, whose authors are Dr. Ravinder Singh and Dr. Dinesh Kumar. So let us start. Structure and bonding. First of all, its introduction. Although most abundant element in the earth crust are oxygen, silicon, aluminium and the other lighter elements, yet strangely enough almost 98% of all living tissues are made up of only carbon, hydrogen, oxygen and nitrogen. Now the question is that the carbon can be the central atom around which the chemistry of life and its processes revolve. The key role in the origin and the evolution of life is of carbon atom due to its disintegrative property of combining and sharing electron with the other carbon atom to form a wide variety of linear, branched and cyclic chain having carbon to carbon covalent bond. The self-linkage property of carbon is called catenation. The force of attraction which bind the atom together in a molecule are called chemical bond. The property of the compounds depend upon the type of linkage present in it. The chemical bond may be covalent, coordinate, ionic, van der Waals and hydrogen bond. Now nature of bonding in organic compounds. Bonding in the organic compounds depend upon configuration of the central atom. The configuration of the carbon atom is that, for example, the carbon atom can form a maximum of 4 bonds, but the type of bond formed depends upon the hybridization of the carbon atom. Second, depend on the hybridization of the central atom. The hybridization of this carbon atom affects the several physical and the chemical properties like bond length, bond energy, acidity, etc. of organic molecule. First is of hybridization. The process of intermixing of atomic orbital of the same atom having nearly the same energy in such a way that they redistribute their energies and give the same number of new orbitals called hybrid orbital of the same shape and energies are called hybridization. The property of hybrid orbitals are entirely different from those of atomic orbital from which these have been obtained by hybridization. Hybridization doesn't take place in isolated atom and the hybrid orbital are formed only at the time of the bond formation. Since hybrid orbital forms stronger sigma bond, therefore carbon atom and the other atom goes hybridization prior to bond formation. Characteristics of hybridization. Characteristics of hybridization involve condition for the hybridization and the property of hybrid orbital. Condition for hybridization. The hybridization takes place during only the bond formation. That is, hybridization never occur in separate atoms. The hybridization takes place using valence atom, that is sp, d and f subshell of the same atom. The hybridization takes place only among orbital having small energy difference. Next one, half filled, completely filled and vacant orbital of an atom can take part in hybridization. The excitation of electron from lower subshell to higher subshell is not necessary during hybridization. Next one, property of hybrid orbital. The number of hybrid orbital formed is equal to the number of atomic orbital taking part in the hybridization. The hybrid orbital formed having identical shape and energies. The hybrid orbital has two lobes, one larger lobe and the other smaller lobe. The larger lobe has more electron density than smaller lobe and thus larger lobe is used during overlapping of orbital. The hybrid orbital forms stronger sigma bond than the atomic orbital taking part in hybridization because the hybrid orbital can overlap to a greater extent. Each hybrid orbital cannot have more than two electrons with opposite sign. The hybrid orbital orients themselves in space at maximum distance apart to acquire minimum interelectronic repulsion of maximum stability. Hence, type of hybridization tell about the shape, geometry of the molecule. Type of hybridization. The hybridization can be of different types, but the carbon atom can show the following three types of hybridization. First is diagonal or sp. The hybridization in which s and 1p orbital intermix to give 2sp hybrid orbital which has same energy and identical shape is called sp hybridization. The 2sp hybrid orbital orients themselves in space at an angle of 180 degree to give linear shape by acquiring minimum interelectronic repulsion, minimum energy, maximum stability. Hence, the sp hybridization is also called diagonal hybridization or linear hybridization. Each sp hybridization contains one electron and has 50% s character and 50% p character. Next one. In the formation of acetylene molecules, each of the two carbon atom undergo sp hybridization to form two sp hybrid orbital which are collinear in condition. In addition, each carbon atom has two unhybrid p orbital which are at right angle to each other and also two sp hybrid, the promotions of electrons followed by the hybridization as shown in figure. On the sp hybrid orbital of one atom overlap with the one sp hybrid orbital of the other carbon atom along their internuclear axis to form a sigma bond between them. The other sp hybrid orbital of each carbon atom overlap with one s orbital of a hydrogen atom along with their internuclear axis to form C at sigma bond. Since all the four atoms, two carbon and two hydrogen, lie in a straight line, acetylene is a linear molecule. The two px orbit, one on each carbon atom, undergo sidewise overlapping to form a sigma bond between to form a pi bond between the two carbon atoms. Similarly, two p y orbital of two carbon atom also overlaps sidewise to form another pi bond. Thus, the two bonds at the right angle to each other, if the electrons cloud of one pi bond is considered to be above and the below line joining the two carbon atom, then the other word lie in the front of and behind this line. In actual practice, however, these merge with the internuclear axis due to which the electron density cloud appears cylindrical and its symmetry is shown in this figure like this. Next one. Various parameters of acetylene molecules are bond angle. Bond angle H carbon carbon is 180 degree. Carbon to carbon multibond bond to carbon bond length is 1.2 angstroms or 120 picometer. Carbon and hydrogen bond length is 1.06 angstrom or 106 picometer. Carbon-carbon triple bond strength is 200 kilocalorie mole inverse or 236.6 kilojoule mole inverse. Parameter for acetylene molecule as shown in this figure. Secondly, trigonal or sp2 hybridization. The hybridization in which one s and 2p orbital intermix to give 3sp2 hybrid orbital which has the same energy and identical shape is called sp2 hybridization. The 3sp2 hybrid orbital are oriented in space at an angle of 120 degree To acquire trigonal planar shape by acquiring minimum interelectronic repulsion, minimum energy, maximum stability, planar shape of acquiring maximum stability. Hence the sp2 hybridization is also called triangular hybridization. Each of sp2 hybrid orbital has 33.33% sp character and 66.67% p character. This type of hybridization explains the structures of all compounds of boons such as bf2, bcl3, bh3, etc. All compound of carbon having a double bond between carbon atom, carbon-carbon double bond, that is ethylene, in conjugated diene or polyenes, that is 1,3-butadiene. Next, shape of ethylene. Electronic configuration of carbon in the excited state is 1s2, 2s1, 2px1, 2py1, 2pz1. In formation of ethylene molecule, each of the two carbon atom undergo sp2 hybridization to form 3 sp2 hybrid orbital. Beside these 3 sp2 hybridized orbitals, such as carbon atoms has one unhybrid 2p orbital which is oriented at right angle to the planar of the 3sp2 hybrid orbital. The process of electronic promotion and the hybridization is shown in this figure. One of the sp2 hybrid orbital of the carbon atom overlap coaxially with the one sp2 hybrid orbital of the other carbon atom along their internuclear axis to form a carbon-carbon sigma bond between them. The remaining two sp2 hybrid orbital of each carbon atom overlap with one s orbital of the two carbon atom along with their respective internuclear axis to form carbon-hydrogen sigma bond. The unhybridized 2p orbital of the both carbon atom overlap sidewise to small extent to form a weak pi bond as shown in this figure. The ethylene is a planar molecule. Various parameters of the ethylene molecules are carbon-carbon double bond length is 1.34 angstrom or 134 picometer. Carbon-hydrogen bond length is 1.09 angstrom or 109 picometer. Hydrogen-carbon-hydrogen bond length is 107.5 degrees. Carbon-carbon hydrogen bond is 121. Now the determination of hybridization of central atom. The hybridization of the central atom can be determined in different ways. First of all, the hybridization of the central atom can be determined by calculating the hybrid state number of the central atom as Hc is equal to 1 by 2 Vc plus Mc minus C plus A, where Hc refers to hybrid state of the central atom, Vc number of valence electron shell in the central atom, C refers carbon on charge on positively charged species, and A charge on negatively charged species. Hybridization of the central atom can be determined by calculating the hybrid state number of the central atom by counting the number of the sigma bond and the lone pair of electron in the given species. Hc is equal to sigma bond plus the lone pairs. Next one is bond length. The average distance in between the center of the two atomic nuclei in covalent atom is called the bond length or the bond distance. The bond length are characteristic property of a molecule and give the information about its structure, properties, etc. Bond length can be determined by X-ray diffraction, electron diffraction, or other spectroscopic studies. Unit of bond length. The unit of the bond length is angstrom. 1 angstrom is equal to 10 raised to power minus 10 meter. or picometer. 1 picometer is equal to 10 raised to power minus 12 meter. Bond length of some common covalent bonds are given below. Carbon carbon gives sp3 bond. Its bond length is 1.54, or its typical compounds are like ethane, propane, etc. Similarly, carbon-carbon double bond. It's give sp2 to sp2 hybridization and its bond length nearly 1.34. Typical compounds like ethylene. Next one, carbon-carbon triple bond. It give sp-sp hybridization. Its bond length 1.20 and typical compounds like ethylenes. Carbon and the hydrogen. It give sp3, sp2 and sp. Their bond length which is equal to 1.1, 1.10, 1.08, and the typical examples like methane, benzene, acetylene. Factor affecting the bond length. Size of the atom. Bond length is directly proportional to the size of the atom. That is, bond length directly proportional to the size of the atom. So we can see that the larger the size of the atom, longer will be the bond length. For example, bond length order among the hydrogen halides such as Hi having greater than B, HBr, then HCl, then HF. On moving down the group 17 hydride, the size of the X atom increases and thus the internuclear distance between the H and the X atom increases. So HX bond length also increases. Now, multiplicity of bonds. It means bond order. Bond order is defined as the number of the bonds present in two covalently bonded atom. The bond length is inversely proportional to the multiplicity of the bonds. So we can say that the more the number of the bonds, smaller will be the bond length. Because with the increase in the number of the bond, the force of attraction in between two atom increases and thus the two atom come closer to each other, so the bond length decreases. The bond length order is that carbon carbon is greater than carbon carbon double bond and carbon carbon double bond is greater than the carbon carbon triplet bond. Next one, type of hybridization. Percentage S character. The bond length is inversely proportional to the percentage of the S character. That is, bond length inversely proportional S character. We can say that more the percentage of the S character, more will be the electronegativity and more will be the attraction with the neighboring atom. So smaller will be the bond length. For example, carbon hydrogen bond length order among carbon hydrogen carbon hydrogen double bond and carbon hydrogen triplet bond. Carbon hydrogen bond give 25 S character, carbon carbon double bond H bond give 33 S character, and carbon carbon triplet bond give 50% S character. Electronegativity of carbon atom. Less electronegativity of carbon atom, because in carbon hydrogen and carbon carbon double bond carbon hydrogen and carbon carbon triple bond, the carbon atom has sp3, sp2 and sp hybridization respectively, and thus 3 occurs more attraction in between the carbon and the hydrogen atom in carbon carbon triple bond and then in carbon carbon double bond and single carbon carbon bond. Delocalization of electrons. With the delocalization of pi electrons over conjugated system, bond length decreases for the single bond with the increase for the double bond. For example, in benzene there are 3 carbon carbon single bond and 3 carbon carbon double bond. The expected value of bond length are 1.54 angstrom and 1.34 angstrom. Actually, in benzene, the delocalization of electron cloud takes place and all the bond length become equals to, that is 1.397 angstrom. Next one, the bond length. The average amount of the energy released when 1 mole of bond are formed from the isolated gaseous atom is called bond length, or the average amount of energy required to dissociate 1 mole of bond present between the atom in the gaseous molecule is called bond energy. We always take the average value of the bond energy because the bond energy of a particular bond is not same in different type of compound and even not same in the same compound. For example, carbon bond, the bond energy of carbon hydrogen bond is not same in CH4, C2H6, CH3Cl and CH2Cl2. Hence we always takes the average energy. Average energy is equal to E1 plus E2 plus E3 plus E4 approx to En divided by the n. The bond strength are usually calculated from the value of heat of formation or heat of combustion using Hess law of constant heat submission. Some of the important bond energy are given in the table. It can be seen from the table that carbon-carbon multiple bond are associated with higher bond energies and thus are stronger than the carbon-carbon single bond. Like this. Factor affecting bond energy. First of all, the size of the atom. Bond energy is inversely proportional to the size of the atom. That is, so we can say that the larger the size of the atom, longer will be the bond length, and thus lesser will be the energy required to break the bond, lesser will be the bond energy. For example, bond energy order among the hydrogen halide HF has greater than HCl, then HBr, then HI. Multiplicity of its bond energy is directly proportional to the multiplicity of the bond. We can say that more the number of the bond in between the two atoms, smaller will be the bond length and thus more will be the energy required to break the bond. That is, more will be the bond energy. Second one, number of lone pair electrons. The bond energy is inversely proportional to the lone pair electron present on the bonded atom. So we can say that the presence of the lone pair electrons on the bonded atom cause repulsion between the atom and the less energy of the amount of energy is required to separate the bond atoms, that is lesser will be bond energy. Now the bond angle. The angle in between the two adjacent bonds emerged from the same carbon atom in a molecule is called bond angle, or the angle which is formed between the lines representing the direction of the bond is called bond angle. The bond angle is expressed in degree, minutes and seconds. Bond angle is determined by the X-ray diffraction experiment and electrons diffraction method. The normal bond angle is tetrahedral angle, that is 109 degree 28 minute. Or further, with each lone pair electron on the central sp3 hybrid orbital, the tetrahedral angle decreases by 2.5 degree. That is, tetrahedral angle in methane is 109.5 degree. The tetrahedral angle in ammonia having one lone pair is 109.5 degree minus 2.7 degree, which is equal to 107 degree. The tetrahedral angle in water having two lone pairs, that is 109.5 degree minus 2.5 degree minus 2.5 degree is equal to 104.5 degree. Factor affecting bond length. First of all is hybridization. Four molecules having sp3 hybridization, the bond length is 109.5 degree, whereas the bond angle for sp2 and sp3 hybridization molecule are 1020 to 180 respectively. Second one, nature of the atom attached. Some hybridization, sometime bond angle derivatives due to the presence of the atom having different electronegativity, that is hydrogen carbon carbon bond in n propane is 109.5, while BRCC angle in 1 bromopropane is 114.2 degree. The changed bond angle, for example, in ammonia, NHN angle is 107. Now, comparison of bond angle in between the compound when central atom is different along with the different number of lone pair electrons but neighboring are similar. Bond angle among the CH4, NH3 and water is CH4 greater than NH3 than H2. Reason, order of repulsion in between the different type. Lone pair is greater than lone pair then bond pair. As there occur lone pair repulsion in water, while lone pair bond pair repulsion in ammonia and bond pair repulsion in methane. So the bond angle decreases to a large extent in water than in ammonia from the tetrahedral angle in methane, and the strength of bond along among the CH4, CH3, H2O is CH4 greater than NH3 than H2O. Covalent bond. The bond which is formed by the mutual sharing of the electrons in between the same or the different atoms is called covalent bond. For example, formation of H2 molecule. Formation before bond formation, 2HH atom, and after sharing there is a bonding between hydrogen and hydrogen atom. Classification of covalent bond on the basis of bond order. First of all, single bond. The bond which is formed by the sharing of only one electron pair in between the two atoms is called single bond. This bond is formed by axial overlapping in between the two orbitals, the two atoms. The single atoms is always a sigma bond or can never be a pi bond because the atom forming single bond prefer to form a stronger sigma bond rather than a pi bond. Second, multiple bond. The bond which is formed by the sharing of the two or the more electron pair in between the two atoms is called multiple bond. It may be double or the triple bond. Double bond. The double bond which is formed by the sharing of the two electron pair in between the two atoms is called double bond. It contains one sigma bond and the one pi bond. Next one, triple bond. The bond which is formed by the sharing of the three electron pair in between the two atoms is called triple bond. It contains one sigma bond and the two pi bond. A multiple bond always contain only one sigma and the remaining other two will be pi bond. Localized and the delocalized bond. Localized. Localized bond are those bonds in which the electron pair do not move from their position. The sigma bond will be localized if it is not involved in hyperconjugation. Similarly, and pi bond will be localized if it is not conjugation with other multiple bond or with heteroatom having positive charge, negative charged odd electron, non-bonded electron present in p orbital. Delocalized. The ability of pi electrons to participate in more than one bond formation is known as delocalization of electrons. Such bond form may change their position with one another. Such bond are called delocalized bond. The delocalization of electron always result in strongly bonded atom, strongly stable bonded molecule having double or triple bond in conjugation. When double or triple bond are present in conjugation in a molecule, then the delocalization takes place. For example, pi bond in 1,3-butadiene are delocalized to give the following structure like this. Then molecule have double or triple bond in conjugation with pi bond of an adjacent atom. When double or the triple bond are present in conjugation with non-bonded electron present in p orbital of a heteroatom, delocalized takes place. Hyperconjugation, it means no bond resonance. Conjugation Consequence of delocalization always decrease the energy of the system and enhance the stabilities. Thank you so much.